Good morning, ladies and gentlemen. Today is the second day of the International Symposium on COVID-19. Now let's welcome the chairperson of the National Committee of CODATA at Academia Sinica, Academician Third-Tai Lee, to chair this session. Let's welcome Academician Lee.
Good morning, and those good afternoon, good evening, those who are online in different time zones. Welcome to this second day and the last session of the symposium. And today we have 6 speakers on session of impact on society. And I would like to remind those who are online, if you have any questions, please get on our Slido platform to post your questions. And also there is a slight change of program. The third talk by Professor John Burrows, originally scheduled, will be switched with the talk by Dr. Hodson. So Professor John Burrows' talk will go second, and then Dr. Hodson's talk will be the third presentation. The first speaker of our session will be Dr. Patrick Yang. He is currently chairman of Ultra Bio and Acepodia. Both are private and clinical stage biotech companies. He's also vice chairman of National Resilience and he was the senior executive vice president of Juno Therapeutics and Hosh and Genentech. Let's welcome Dr. Patrick Yang.
Thank you very much, Mr. Chairman, and really appreciate this opportunity to share my perspective. My title of the talk is Health and National Security, and the subtitle is The Impact of COVID-19 on the Global Biotech Industry. So in an ideal world, medical care and medicine should not have politics. Unfortunately, that's not the case today. Medicines and vaccines for COVID-19 are being used as tools and weapons in both domestic and international politics. So we, the practitioner of this industry, really are facing the issues with a very heavy heart, because doctors should have no borders, and scientists should have no politics. Scientists should be nonpartisan. We should give our opinion, make our decision based on data, black and white, and not because of the political colors. But the real world is not the case. What we learned from this pandemic, very painful pandemic, the US has been in lockdown for 7 months now. And what we learned, the 2 fundamental truths we learned about the industry: resilience of the domestic supply chains is crucial, it's critical to national security. Health is a national security issue. The second thing we learned is that complex medicines are the future of the healthcare. From the COVID-19 pandemic, governments and private investors are funding a lot of technology programs that would otherwise take years or maybe decades to fund. There's been a lot of funding coming into very complex technical platforms to produce both the vaccines and the treatment for COVID-19. So we're still grappling with the uncertainty of this pandemic. We are still learning about the virus. We learned a lot since January, but we still haven't really come to a full understanding of when we could bring this virus under control. When will this end? We don't know. We thought earlier this year, we thought the summer would take care of it. And by this time, we'll be back to normalcy. That's not the case. Where will work get done is a big question, because before this pandemic, we, the business people, value co-location and the proximity for your business. And the pandemic proved that you actually don't have to come to your workplace every day. You could telecommute. You could practice telehealth, telemedicine. You could do teleconference all day long. And you could conduct a business without being there with your colleagues. Of course, that could not go for too long. And we believe that the human touch is still required for us to have teamwork. In the US, what we've seen is a reversal of urbanization. Before this pandemic, young people are moving into the city center in just about any metropolitan area in the United States. This pandemic had created a reversal, at least a temporary halt and reverse of that urbanization. I've had quite a few occasions, about a dozen occasions, when I was on video conferencing with consultants, with other company employees, and then I discovered that they have left New York City, they have left Los Angeles, and they moved to the mountains of Utah, the mountains of Montana, and they're calling in with the virtual background that make it look like they're just in the office or in the city of New York. So where work is done will be a huge impact by this pandemic. The other thing that this industry had taken a hit is that at the beginning of this pandemic, we saw the supply chain were so fragile, especially in medical supplies and medicines as well. The supply chain, we were globalizing supply chain. Large companies are outsourcing their APIs, their drug substance from countries like China and India. So we were indeed globalizing. We thought that the world is going to be flat. We could compete from anywhere. That has changed suddenly into a nationalization. Countries, not just the US and several countries began to think, how should they control the supply chain in the next pandemic? The other thing that we learned that's a huge impact is the technology. So countries, governments are now much more sensitive to exporting technologies, not just the high tech, but also biotech. All these outsourcing, transferring of technologies are being questioned, whether it's the right thing to do. So the next generation biotech platforms or modalities were actually underway before the pandemic. But as I said earlier, the pandemic thrust forward a huge amount of funding that accelerated the development. Here's an example of 8 different platforms that we are using to produce the COVID-19 vaccines. So I worked for Merck and a company in New Jersey for 11 years in the 90s. Merck was one of the best companies in vaccine. But back then, we used the good old attenuated live viruses or inactivated viruses, which takes a long time. The newer technologies were under development, but all of a sudden they leaped forward. So the protein subunit, viral vector, the DNA, RNA, all these new technologies came out, and we see the huge progress that's been made. I myself, because of my experience at Merck, I remember the 4 vaccines that were launched in the 2000s when I was there. Each one of them took more than a decade. And the phase 3 usually was a huge trial. So For COVID-19, we've been asked to compress the time from decades, from year to month, and we've been asked to do things quickly in a tenth of the time. So I myself think that a good vaccine that should be effective and durable and should work for all ages. And that good vaccine will probably come in the summer of 2021. And the post-COVID-19 biotech industry will see that the over-dependency on China and India or source sourcing of critical medicine will be corrected. We'll also see, because of the huge fundings for these new modalities, we think that these modalities will become practical and become typical platforms for the future. Manufacturing technologies and capacities are under spotlight. Today, all the companies that are developing COVID vaccine and treatment are looking for capacity in manufacturing capability. I think you've heard or read about President Trump's treatment by the antibody cocktail, and he received 8 grams for that treatment. And if you have 1 million people receiving that cocktail, you will need 8 metric tons. If you have 10 million people around the world treated, you will need 80 metric tons. And the world does not have that kind of capacity today. So we're going to see post-COVID-19 a lot of investment into manufacturing capacity and capability. So in the future, I think we'll see the balancing of where we make the drugs, the supply chain. And the US definitely will be protecting the supply chains. And today, about 70% of the drug substance are sourced from China or India. You'll see that change. The pandemic woke up the regulators and the leaders of the country. They realized the extent to which China dominates the supply of drug substance and chemical. There'll be an effort to balance that. So there's a surge of funds to support vaccine platforms, which will spill over to the adjacent therapeutic areas. That's what we will see. And the business opportunities for the countries, one is tele-everything. We discovered we actually could do things remotely, much more effectively than we thought we could. And the new biotech waves will come. The AAV, the lentivirus, the adenovirus, all these viral vector therapies will come. The advanced complex monoclonal antibodies will get more funding and more work. Vaccine manufacturing capacity will get funded. And then because of RNA, it's so difficult to make. New technologies such as microfluidic, chip-based manufacturing, they are coming. These methods are coming. The factory of the future will be on a chip. They're no longer 10,000 liter stainless steel reactors. You will be able to perform at the cell level through microfluidics and laser tweezers with the assistance of AI and machine learning. You could actually perform 4 bioreactor processes on a chip that's half the size of your smartphone. That day is coming. And I think that the folks in Taiwan have lots of capability in competing in this. So this is an area that you will see a lot of opportunities. So, and the best way for us to predict the future is really to create it. So let's create that future. Thank you very much.
Thank you very much. I would like to welcome questions. Any questions on the floor? Okay, please.
Hi, Pat. Futong Liu,
Hello.
Vice President. So thank you very much for your very insightful presentation. So I have a question about vaccine. You mentioned about that, and in Taiwan, as you know, we have 3 companies currently working on vaccine. they all, I think they all have gone into phase 1 trial in Taiwan. And so, but when you go to phase 3, obviously need to a larger number of people, and also need to be done in a place where COVID-19 is still endemic. So do you have an advice on this aspect?
Sure.
Yeah.
Sure. Pudong, first, thank you for inviting me. This is an honor to speak to you. In the situation of Taiwan, it's challenging because the COVID-19 vaccines are being developed with all kinds of platforms around the world, and we cannot ethically we cannot do challenging clinical trials. So you have to dose the patient, or in this case, not patient, subjects, and then you have to observe them in the communities to see if they get the diseases. Taiwan has done such a great job. In fact, Taiwan is the best in fighting COVID-19 with the containment and the contact tracing and testing. So this really gives Taiwan a huge disadvantage of developing vaccine, because you're going to have to conduct the testing in countries, in communities where there are community spreads. So you have to go to other countries where there are more cases than Taiwan. You simply do not have enough cases to come up with statistically significant answer as to your vaccines that you're developing. Around the world, there are hundreds of vaccines being worked on. There's over 55 in the clinical stage, and there's about a dozen in phase 3. A couple of them have been quote unquote approved for at least the controlled use. So we will see vaccines by the end of this year, probably coming from companies like Moderna, Pfizer, J&J, and AstraZeneca. We don't know whether the vaccines that are approved this year will be effective, durable, and will work for all ages. And we won't even know whether there's going to be adverse effect, because to develop an oncology drug, you know the drug will be used on probably 100,000 patients in the first year or the first few years. In vaccine, you're going to be injecting the vaccine to healthy people. Many of them are children or older folks, and you're going to do that with 100 million doses right away. So any problem, 1 ppm would translate into a huge problem for you. So my advice is that you cannot lower the development standards. So today I see that there is a lot of regulatory flexibility, but not in the reduction, the lowering of the standards. There's more flexibility in other controls and regulations, but not in the standard of the vaccine. There is a huge amount of collaboration in the industry, and I'm really pleased to see that. The clinical enrollment in the US and Europe have been done very rapidly, so there's just a lot of volunteers. People really wanted to help. And then finally, we do risk manufacturing. So most of these companies that I mentioned began their manufacturing at the beginning of phase 3. They don't wait until they have final data. So it's going to be a challenging task for Taiwan, but we have to do what we have to do, because in the end, every country would want to have their own vaccines under their own control. So, and this virus will be with us for at least 2 more years, maybe 3 or 4 years. So we have to develop our own vaccine, but it is challenging because the area where you conduct the clinical trial would have to be outside of Taiwan. Thank you.
Thank you. Are there any other questions from the floor? Yeah, if not, I think we'd like to move on. Thank you so very much, Patrick, for your excellent talk. Yeah, thank you. Move on to the next. So the next presentation will be given by Professor John Burrows. He is with the Institute of Environmental Physics, University of Bremen, Germany, since 1992. He is Professor Burrows, best known for some pioneering and innovative developments in remote sensing of atmospheric trace constituents from ground-based, shipped, and in particular space-based platforms. Professor Burrows was seconded from between 2008 and 2010 to be the science director of biochemistry at the Natural Environmental Research Council of UK, and where he becomes a fellow in 2010. Let's welcome Professor Burrows.
Can you also see my slides?
Yes.
Okay, then I'll begin. Okay, well, first of all, I'd like to thank you again for inviting me, and thank you for sorting out the technical problem. It was probably, I hadn't quite correctly joined. Okay, so I'm going to talk about some impacts of COVID-19 on our atmospheric trace constituents observed from space. And this is the European Sentinel-5 precursor, which is the latest European mission, enables us to do passive remote nadir sensing from space of trace gases. So this is spectroscopy, absorption spectroscopy, essentially nadir looking. And I'm going to concentrate on this. I'd like to thank my co-authors and helpers who provided some information, different slides to this talk. Okay, so my first slide is just to remind you that the problem that we've got is that we've got an awful lot of people on the planet now, three times the amount when I was born in the 1950s, and we're now at 7.8 billion, and actually a large number of these are in Asia. Here's the map of the world. Here's the map of the world with its balance towards population or weighted towards population. And so you can see how dominant Asia is. So what Asia is doing is extremely important in terms of producing emissions to the atmosphere. Now, as this is a transdisciplinary talk, I just want to point out here that this is a lot of processes going on in the atmosphere which make essentially ozone and aerosol as sort of end products, as so-called secondary aerosols or secondary pollutants or short-lived climate pollutants. And 20 years ago or 30 years ago, we knew none of these cycles, but now we do, and we can actually predict and test our understanding by making measurements globally. And this is what we're actually able to use in COVID because we've got a very unusual situation where a lot of emissions are being reduced. The question is, can we then test our theory? Okay, so a lot of different processes going on there, but it's essentially mankind and the biosphere, including the ocean, emit substances, primarily hydrocarbons and oxides of nitrogen and such things. And this mixture makes this smog, which you can see here pictures of going back in history. We have the winter smogs in the UK, which are very famous. We have the Great Smog of '52. And nowadays we have summer smogs first found in Los Angeles, now all over the world, a mixture of summer and winter smogs. Winter smogs are more acidic, SO2 based, and summer smogs are more ozone, oxides of nitrogen based, with a lot of aerosol in both of them, which is why you can see very little in these pictures. You see an Eiffel Tower in the background in Seoul. You see the very nice historical buildings, and even in a place as clean as Spitsbergen, which is in the Arctic, you get these episodes of Arctic haze, which are not dissimilar to those in cities. Okay, why is this particularly bad? Because, of course, we breathe it in, and it affects our respiratory system, or it goes into our respiratory system, and the cardiovascular system responds in negative ways. It can even potentially get pollution into the brain. Now, of course, this is the same system which is bringing in the COVID, but I'm talking essentially about outdoor aerosol here, and not about the indoor, which is the main way of transmission of COVID. But this is the estimate of deaths just from outdoor aerosol, and so that's a very significant number and a great reason why we are working on these understanding aerosols and ozone being made in the air. Okay. So why do we want to observe from space? Well, the simple matter is we've entered this Anthropocene where we're changing the composition of the atmosphere. Well, what we need is early warning, and so we need a global observing system. And this is done from space, and we do this either in geostationary or in low Earth orbit, as depicted here. And essentially the low Earth orbit got going. I'm going to talk about main low Earth orbit data today, which gives us in polar synchronous mode primarily, which means we get one measurement or possibly two measurements a day, a single satellite. In geostationary, we look at one part of the world and are able to see maybe once an hour or maybe once half an hour, depending on sampling strategies. So the combination of the two provides this global system. Now, ideally, we have measurements then maybe twice a day from a LEO, and then the rest of the time from a GEO. So we get a nice sampling strategy, but we need quite a lot of GEOs to then cover the whole of the world. Now, I'm talking about passive remote sensing, and this is using the absorption spectroscopy in the UV visible and near infrared, short infrared regions. And these are primarily electronic vibrational spectra, which enables to measure the species which are listed here, and through their absorption and aerosols by scattering. Okay, now current world is here in terms of we've been doing this about 30 or 25 years or so, and we're currently, I'm just pointing at it, the SP5 is an important satellite for this presentation. The Sentinel, the so-called European Sentinels, but we're slowly getting, it looks a lot better than it really is perhaps here, because trying to improve sampling to be able to make measurements that we need to have. So that's a little bit of the background. And let me just go back one. Yeah, no, that's okay. This is the, there's also, this Sentinel-5, this is a history since 1985, and we're now up here and improving our system. But what are data? Okay, so the driver for this is that we've been trying to control policy on air pollution since at least King Edward I in England, and we have international policies like the UNECE Convention on Long-Range Transport. Currently, that's called CLAP, and HTAP is the current process of assessment. But what is COVID doing? Well, it's changing human behavior, and this results in less emissions. We've had some clean air periods in Europe, which we didn't expect to have. And we're changing the production of these secondary aerosols and ozone. Okay, so these two nasty species are not being made. We've got a lot of other byproducts, which are not so good, like PAN, things like this. And we're also changing the long-lived greenhouse gases. And this is a unique opportunity to test our understanding. Just to say how we measure, here are some spectra of NO2. These are from SkyMatch, actually, but we see a fit NO2. It's differential spectra here. We see fits of ozone, and you can see they're very good. And we need very precise fitting because we have to understand the troposphere, which is only part of the Earth's atmospheric burden. But here we see pictures of from 2011 of NO2 from SkyMatch, and we're able to see pollution periods and places, biomass burning, also shipping even, and We see soil emissions and also transport pathways. And if, for example, you take China, one thing we've been doing for a long time now is look at the changes in China. On the bottom right-hand side, you can see the long-term average over we call central or eastern China. And at the top, you can see the changes after introduction of pollution control measures. So it's come down quite a bit in the last year. And overall, what we can say is we had an increase and we've now decreased. So the question is, what's happening to this in COVID period of time? That's the background. Okay, we can also do SO2. I'm going to jump ahead on this and jump to one of the problems, perhaps I'd like to say of what we're seeing is this looks like a very big change. And there is a significant change. This is sort of down to the lockdown. And these are the type of pictures which were from Sentinel-5, but which are being shown earlier this year to demonstrate pollution change. And it all looks very good, but I think it's a little bit, what we're forgetting is the actual changes of NO2. And here we see NO2 changing in offline products over China. And the idea that there is a difference, but it's not quite as big as what you're just seeing. And I think that's important to discuss. And here we see in January, March, April. But I'm going to jump to saying that we saw a rebound, but I'm going to bring that together now in this easier to understand plot. And this is then the NO2, and this is going from 2018 to the beginning of 2020. And what we're seeing, if I move to the screen, is that we're seeing differences in years, and there isn't a large amount of natural variability. But on top of that, we're seeing the impact of the shutdown, and that's the difficulty for us to pull out. So some of those more dramatic pictures are natural variation, and we have the same problems in Europe. Here we see again the difference in this case between March in Europe. We were slower at locking down. That caused a lot of problems. We can see decreases, but if we go, for example, to northern Italy, again, you'll see this problem of understanding the differences between February and March. And here's the actual Po Valley blown up, and we are seeing differences. But again, we're on the background of things that are happening anyway. So some of as I said, the more dramatic changes are a little bit way down. But we are able to see changes. Here's the Rhine area in the same way. We're seeing differences, and we are seeing the impact of the reduction in this lockdown of our pollution. Okay, and here we can compare European NO2 differences in March and April. And we've got significant differences, but the picture is rather complex, and that's the message to get across. Situation in the USA is we didn't see very much going down in comparison to Europe or Asia. That probably reflects that transport and stuff was not down that as much in comparison. Okay, so what about aerosol optical thickness? For this, we're using the GOSI and Olshi data from our side. So this is a collaboration with our friends in Korea. We've been looking at this, and here you can see now the OD changes in January, February, March averaged over the years, and you see the 220, and you do see differences, but it's actually a mixed bag because some places are increasing and some places are decreasing. And this is the message that I want to get over. Again, it's a complicated picture, and it's based on also what's happening naturally. So we do see some impacts of social distancing as shown here from the Chou et al. Paper now in submission by our Korean friends. And what I can say is that they're saying what's happening in April, and what we're seeing is both increases as compared to previous years and decreases induced by the lockdown. Okay, that's the take-home message in general, and that sort of agrees with this analysis of the NO2 data, again, averaging. So when we look at average pictures, we see a change from the average, particularly in February and in China. Okay, and this is now a comparison of the Sentinel-3 AOT data, and what we see is the difference between January and April from 2019 2020, and again we see increases and decreases. That's exactly in agreement. Here's the same situation from the MIRA, which is a data assimilation product, and for the, in this case, PM5. So we're seeing both increases and decreases, and that way to understand a mixture of changes in emissions and changes resulting from the lockdown. And what you can see here is our LEO and GEO actually agree quite well. So two independent showing the same picture, AO2. Okay, now, just looking ahead, I'd like to say that what I'm going to do now is look at the CO2, and we're hoping for this new mission, but at the moment we're using CO2 and GOSAT. So these are great experiments, and we can do long-term changes, starting with Saimaki. Here's the CO2 change, which has a seasonal cycle on it, related to the release of CO2 by dropping of leaves, and then the uptake of carbon to the trees, and that seasonal cycle. We can do that very well. And these two satellites are now making the current measurements, and we're measuring XCO2, which is the dry mole fraction, and we've actually, in this case, done a daily anomaly because we're going to have to do some statistics here, and we're using the following ensemble of analyses. That's 4 data sets, okay, from different partners of ours around the world. And when we actually come to it, this is then our differential so-called daily anomaly map. Okay, so 0, no change, and we're seeing, this is what we're seeing in general. And I'm particularly interested in the current period of time. When we do an analysis, we're actually seeing this is CO2. So what this map tells us is that indeed over Eastern China, averaged over this box from 28 to 44 north and 102 to 126 degrees east, we're seeing this rather dramatic change. But I have to say is the current global system is within the error bar. So the mean of our ensemble is giving about the right amount of change to what we expect from our knowledge of what's going on in China on the ground. So we are seeing it, but it really says we need to go forward to our CO2 measurements, which are planned for starting in 2026, where we have much better coverage. Okay, so just to summarize that, our 4 CO2 data products are providing this unique opportunity to look at it, but it's rather touch and go between whether or not it's really there or not. What you have to remember is that changes are very small on a large background. However, we are able to just about see that's change in CO2. So that paper's also gone off. Okay, last but not least, to show some complications, we're also looking at methane. We see that quite well on average, looking at global data, seeing the increase and decrease of methane. But when we look at, for example, China, we see a mixed picture, and this is because of different sources. It's not very clear what's happening between the difference between 2020 and 2019. And similarly, when we look at CO, we'd expect CO maybe to have gone down, which it has done in the Beijing region, but this is down here in the Southeast Asia. It shows changes of biomass burning, and we're seeing actually increases, for example, over Taiwan in this period. So overall, we have a lot of challenges ahead. Okay, and in the near term, we're using the instruments that we have. We're going to get some new ones up in the near future, and that will help and improve our ability to look things. I think I'm going to just show, this is a state-of-the-art picture from California where we're able to see from space. But when we fly over the same area, we'll see it much better. Okay, so for the future, we need this 1 by 1 kilometer. That's coming, but we have many challenges ahead. And I'll just summarize again by saying I think we need to improve the global system, but the satellites are already showing tremendous ability to probe changes, which, for example, are being incurred by these lockdown. And this is an experiment which is going to go on for the next couple of years, I think, because I don't think we'll be out of this for a while. So this gives us a great opportunity to test our knowledge, and we are indeed seeing changes from space of some of these key constituents, in particular CO2, NO2, and AOT. Thank you very much.
Thank you very much, Professor Burrows, especially you during wee hours of where you are now. We are open for questions. Are there any questions on the floor? Please.
Well, John, thank you for the nice presentation and sharing your knowledge with us at such an early morning at your time. And my question is, in your observation, after the so-called reopen or, you know, resume all the social activity in Europe, what's your observation in the changes of air quality in Europe?
Okay, well, this is obviously ongoing work, but we have seen, what we've seen in Europe is a decrease of maybe, you know, the order of 10% of NO2. We have seen, I think, also some AOT going down. But actually the impact, when people lock down, they're also producing pollution from home. So traffic is down. But other sources are also maybe a bit up. So that in the balance, when we go into lockdown, we're seeing changes, but they're not, you know, they're not as, they're significant in that we're seeing, you know, different types of air, but it's not, it's observable, but it's not like a factor of 2 or anything like that. It's more like, you know, 10, 15% of NO2 down. And NO2 seems to be the best indicator because it's rather short-lived. Nitrogen dioxide has a short lifetime in the atmosphere, and therefore you see pretty instantaneously the changes. But for example, CO2, that's very long-lived, and so we are seeing a change, but they're rather small as a result of the lockdown and the reduction. But what we're able to see from space, we are, with the current generation, we're able to say, yeah, we can see this about. But what I'm suggesting is that as we move forward in the global living system stakes, by the 26-27 period, we'll have much better CO2 measurements in terms of spatial resolution and their sampling, okay? Temporal sampling as well, I'm hoping that we have enough, but we are moving forward in this, and this is what gives us hope for the future, that we will have a system which is really able to pinpoint anthropogenic changes. Okay, does that answer your question?
Yeah, thank you.
Thank you so very much for your presentation. I think that due to time, we will have to close this session. Thank you again very much for Professor Burrows for staying up so early in the morning. Thank you so much. So let's move on to the third talk by Dr. Simon Hodson, who is currently the executive director of CODATA. He is an expert on data policy issues and research data management, and he has contributed to influential reports on current best practices for research data management policies and to the Science International Accord on open data in a big data world. Let's welcome Dr. Simon.
And I'm very pleased to have received this invitation to speak to this international symposium convened by CODATA Taiwan and the academic at Sinica. My topic is Making Data Work for Cross-Domain Grand Challenges, and that's the title of an international program of a duration of 10 years, a decadal program, therefore, that CODATA is preparing on behalf of the International Science Council to address fundamental data issues for particular domains of science and for those cross-domain challenges. And the relevance of that topic and of that program for this symposium, I hope, will become readily apparent. So, CODATA, of course, as I'm sure many of the participants will know, is the Committee on Data of the International Science Council. We are more than a committee. We're a not-for-profit, international and global organization whose mission is to connect data and people to advance science and improve our world. Of course, we're part of the International Science Council, and therefore we support the ISC's own mission of advancing science as a global public good, and we do so specifically by promoting open science and fair data. And I'll go on to talk a little bit about fair data in particular. We convene a global expert community and provide a forum for international consensus building and agreements around a range of data science and data policy issues. And I'll talk very quickly now about some key elements of our strategy. When we're discussing our strategy, we talk about these four principal areas of activity. We do work in the realm of data policies, and we have an International Data Policy Committee, and in each year in the past 5 to 6 years, we've produced a major report or policy statement on a variety of issues. We do work on data science. We have task groups and working groups. We have a data science journal, and we regularly organize conferences on various technical and scientific issues relating to data science. We do work on data science, on data skills and education. We have a program of research data training activities in partnership with the Research Data Alliance, and also we regularly organize with partner countries, for example, with CODATA China, with our PAST-D task group, training activities in various aspects of data skills. And then finally, we have this fourth column, which we call Data to Improve Our World, and that comprises our strategic executive committee or secretariat led activities, including the promotion of open science platforms and the preparation for this decadal program, Making Data Work for Cross-Domain Grand Challenges. So I'll go on to talk about that. With the merger of what was ICSU and the International Social Science Council to become the International Science Council, ISC has prepared an action plan for the next few years, and a key part of this action plan are a number of projects addressing strategically important issues in global science. In the category of those projects addressing issues of the digital revolution comes the program that CODATA is preparing, Making Data Work for Cross-Domain Grand Challenges. The premise of that activity is that the major pressing global scientific and human issues of the 21st century, things like climate change, adaptation and mitigation, things like the growth of our cities, things like the reduction of risks of hazards, things like our confrontation with the current global pandemic. These human and scientific issues can only be addressed by research that works across disciplines and domains to understand complex systems, and which also employs transdisciplinary approach to turn data into knowledge and then into action. And I'll say something more specifically about that later in the presentation. So the digital and data revolution presents us with huge opportunities and significant challenges. And some of the solutions to those challenges lie precisely in the way that we use data, the way that we collect data, that we curate and steward data, and that we apply those data in our science and in the development of solutions. So the program is about that input from data, about ensuring that we can look after data more effectively so it's more usable and can be more readily combined with other data to address these complex challenges. And I'll say a little bit more about that. The strategic importance of this issue should come as no surprise. For a number of years, the International Science Council, with other organizations, has sponsored global grand challenge research programs, things like Future Earth on global sustainability, integrated research on disaster risk, precisely to combine cross-domain research to mitigate disaster risk. The relatively new program on urban health and well-being, which takes a systems approach, a cross-domain approach. These are major grand challenge research areas. They're aligned with the UN's program and priorities, things like the Sendai framework and the Sustainable Development Goals, and they're of fundamental importance. And they each face a number of challenges, which is that of encouraging genuine collaboration across domains, and that of mobilizing data so that it's sufficiently usable for the science to address those challenges. Now, one of the tools that we have at our disposal to improve the way the data is stewarded and is usable are these things, the FAIR principles. The principles that data should be findable, accessible, interoperable, and reusable. And those principles provide as well a practical guide to how to achieve these things. At this point, I'm going to stop showing my camera so that you can see the screen better, and I'll go on to discuss in more detail the FAIR guiding principles. This is the reference to the detail of the FAIR guiding principles. I'm not going to spend a lot of time on this slide, but I'll also provide you there with a reference for a report that I chaired, produced by the European Commission, which is really a systemic response to the FAIR principles and lays out an action plan and a program of work for the European research area, and in particular the European Open Science Cloud, to respond to adopt the FAIR principles and to turn them into reality. Now, please have a look at the original article on the FAIR principles. There's a lot of detail about how to put these into practice. They cover issues of findability, to have sufficient metadata and a unique participant identifier to enable discovery, of accessibility, so that the data can be accessed, of course, by humans and downloaded in what's effectively a traditional manner, but also to provide programmatic access for analysis so that we can start realizing this objective of greater analysis at scale across large quantities of data. Programmatic access by machines is essential for that. And then these two particularly challenging areas, that of interoperability. How do we get different data sets to work together effectively? How do we know that the phenomena being observed or measured are being observed and measured in the same way? Are the measurements commensurable? Is, in sum, the data interoperable? And then also the issue of reusability. Do we have a license which says how we can reuse them, but also do we have sufficient and rich and accurate metadata for us to understand the data, for us to be able to interpret it, and the provenance data, so that we know what has been done to the data, how it was created, what transformations it may have gone through, so that we know that
Yes.
it can be combined effectively with other data sets of similar type. So these provide a framework for how we can improve the way in which data can be combined for research within a particular domain and for cross-domain research. So in the program that we're preparing on behalf of the International Science Council, we take the FAIR principles and we try to apply them in specific ways as follows. The program design identifies 3 broad areas of activity. Item 2 there is to work with particular domains, particular research areas, to encourage the adoption of good practice and the improvement of interoperability and reusability of data within those domains. And of course, there, one of our principal agents of collaboration are the international scientific unions and associations that are members of the International Science Council. Item 3 there is to take those advances, that good practice, and to try to apply them to cross-domain case studies. And we've identified a number of pilot case studies already that we're working with, those of resilient and healthy cities, of disaster risk reduction and infectious diseases, and more on that later. And then overarching that is the program work, and a program of technical and consensus building activities to encourage interoperability and reusability of those data. I'll say a little bit more about how we're preparing that program and aiming to put that in practice. So through a series of international workshops and some very intensive workshops held at the Dargstuhl Center in Germany, we've prepared this program design and we've initiated a set of pilot working groups and activities. And they're listed here on the screen. The first 3 are particular technical areas that we're looking at. We have a task group on digital representation of units of measure, and that's seeking to collaborate globally with a number of major initiatives, including an initiative of the CIPM to develop the digital SI. We've also got work on semantic interoperability and conceptual frameworks and preparing recommendations on good practices for semantic resources, how those resources are presented technically, how they're governed and sustained. And we've also developed a very good collaboration with the Data Documentation Initiative and their new metadata specification called CDI, or Cross-Domain Integration, which is specifically designed to assist with this process of integration of data from different sources and across domains. It's a metadata specification which is designed to sit over other metadata specifications in order to help with interoperability and data combination. So those are the 3 pilot technical activities. In the program there will be more, but this is what we're putting in place already. And then there are 3 activities which are case studies to look at the implementation of that technical work in particular cross-domain case study areas. For example, we're working with on a suite of activities which we call policy monitoring indicators, looking at data for the SDGs, data for Sendai. We're also doing work on infectious disease data, which I'll speak about a little bit shortly, and for resilient and healthy cities. I'll say a little bit more about the CDI collaboration. The Data Documentation Initiative is a long-standing organization which has produced a suite of metadata specifications, largely principally for the social sciences and for those areas of the social sciences that use survey instruments. And the DDI codebook and DDI lifecycle specifications are widely used in social science data archives around the world. It really is the recognized global standard for those areas of research. increasingly, those data archives are conscious that their users need to combine the principal data sets from social science surveys with other data sets. They could be census data, they could be statistical data, they could be health data, they could be other sources of data. So to respond to that need, they've developed this draft specification called cross-domain integration. That specification is currently open for review, and there's information about that on that bit.ly link, DDI-CDI webinars. We've been running a series of webinars, and now we're launching into a set of more intensive virtual workshops to explore and to test how the specification can be used as it's intended for cross-domain research areas. Upcoming workshops include one on representation of units in collaboration with DRUM, which I've already mentioned, on provenance and making sure that DDI, CDI can deal with enriched provenance information as it intends to, and case studies on environmental sciences and health and medical use cases. I'm going to now spend 2 slides to talk about some of the pilot activities in particular case studies. One of these is a working group which is seeking to explore how to combine social science data from health and demographic surveillance systems with clinical data from specific patients. This relates to a project now called Inspire, which builds on a previous project called Alpha, which is a partnership with the London School of Hygiene and Tropical Medicine with a number of health and demographic surveillance system centers across the African continent. Through those projects, the partners have developed a secure data system. They're applying consistent semantics and metadata, and also with the new CDI metadata specification, they're seeking to apply that in the process of combining those 2 data sources. The large cohort health and demographic study data and specific data on specific patients and their clinical data and their health outcomes. Now that process of combination requires linking a number of data sets, and as I've said, the application of consistent semantics and metadata. That project is underway, but we're now seeking to expand that approach to COVID data. And the lessons that we learn from that activity, we will feed into the decadal program and publish as a set of recommendations. And I hope you can see, just with that brief explanation of what that activity is, how relevant that is to the current pandemic, how those challenges of combining social science, survey data, information about people's lifestyles and health with the specific clinical outcome data, how important that is for addressing health issues of all sorts and in the context of the current pandemic. One of the other case study working groups is looking at urban health and well-being, and it's specifically in partnership with a number of research projects around the world and a number of cities, but also with the ISC program on urban health and well-being. As part of that working group, we're exploring a number of issues and a number of topics, but at the heart of our activity is this development of a conceptual model for a data knowledge action system that can be applied effectively to cities. So the colored boxes there represent the data sources in relation to particular challenge or issue areas understood by cities. And there are a number of ways in which we could break down those issues, but those indicate a number of issue areas which have been identified by the International Society for Urban Health. Now, those issue areas, the data relating to those issue areas depends upon the sort of questions we ask and the sort of data collection program we have underway. So one of the things that we want to do with that working group is to understand and to use a number of case studies to apply a process and a methodology. What are the questions we're asking in those issue areas? How are we going about gathering the data? Where are the data gaps? Where are the shortfalls in the way that the data is described and therefore can be effectively used? So there's a data aspect to this approach. Then we want to explore how we turn those data into knowledge and action, and using a number of methodologies related to interdisciplinary collaborative modeling. That can be data-driven. It can be driven by a form of workshopping and focus groups with community inputs and expert inputs, or it can be done with a combination of those approaches. And that's what we're going to be exploring also. And then the outcome of that modeling should feed back into the system, as the diagram indicates. Through that working group and through this activity, and above all through this collaboration with the ISC program, we want to develop this draft model into something robust that can be easily applied in city systems and can create an intelligent feedback loop from the way the data is gathered, through the way the data is described and made fair, through its input into the collaborative modeling exercise and its feedback into policy and action. And by combining the human dimensions and the data-driven dimensions, we hope to make that process as dynamic as possible. At the moment, we're planning a series of activities for the working group, including, we hope, an intensive workshop later in 2021, which will feed into some of the activities at International Data Week, which I'll go on to talk about. So in preparing the decadal program, we're reaching out to particular, or to deliver the data program, the decadal program, we need particular delivery agents and activities. I've spoken a little bit more about the activities so far, but the delivery agents will be, as often in a global program, a coordinating office and secretariat. For this sort of work, we need, in particular, a cohort of metadata and ontology experts to guide that technical work, and a set of distributed program officers or partner projects. We're currently preparing a call for the management committee, and that will be followed by calls for participating projects or program officers. And we hope to use this program to coordinate and to mobilize a set of action globally, and we're reaching out to all CODATA members and ISC members to participate in those activities. I've described 6 of the initial areas of activity that are already underway. They will proceed and expand through consensus workshops, through intensive sprint workshops. I've mentioned the intensive workshops that we've already been running at the Dargstuhl Center. We want to identify further issues across domains, and we're very open to hear of additional issues and from partner projects who would like to collaborate with the program and its approach. We will formally launch the program, and by which time we hope to have an initial program office and some pilot projects at the ISC's General Assembly in October 2021. And please, we'd very much like to collaborate with CODATA Taiwan, with the academic at Sinica, and with other research institutes in Taiwan on this activity. I'll close this presentation by flagging some upcoming events, which I think will be of interest, and in which we'll be talking a lot more about the decadal program, which is in the process of preparation. First of all, the Fair Convergence Symposium. This is a collaboration with the Go Fair initiative. It's taking place fully virtual, of course, between the 30th of November and the 4th of December. We're organizing the sessions so that on each day there will be sessions which are Eastern Hemisphere friendly, Western Hemispheres friendly, and sessions which we hope that, notwithstanding antisocial hours, most people will be able to attend. This deadline for the session proposals has ended, but there is the call for posters and lightning talks is still open, so please follow that link and find out more about that and consider putting in responding to the call for posters. And please register for the event and participate. There'll be a lot more about these issues of fair data, of interoperability, of reusability, and about various activities building towards the decadal program that I've been discussing. And of course, what we're planning, a lot of our activity is planning towards the ISC General Assembly in October 2021, and of course, International Data Week 2021, which is taking place in Seoul in the Republic of Korea in November. The theme is Data to Improve Our World, and we'll be pulling together a number of the themes that I've mentioned into a major global data event, and we hope by that time that some of the travel restrictions on the pandemic will have finished. But whatever the circumstances we find ourselves in, this conference will go ahead, perhaps in a hybrid format, but we certainly hope that colleagues and partners from the region will be able to attend. So please put this in your diary. There'll be more information about the themes, keynotes, panels, and how to propose a session in due course. Final slide, this is information about how to follow CODATA and to get in touch, the website, the news lists, the various activities we have on global media, on social media, and I thank you very much for your attention. In this format, unfortunately, I can't respond to questions, but please do get in touch if you're interested in the decadal program or either of the conferences that I've mentioned. Please do get in touch and I'll provide further information. Thank you very much.
Okay, thank you very much. Yes, as Dr. Simon Hodson said, he's unavailable. So if you have any questions, please go to the Slido platform.
Ladies and gentlemen, now we'll start the session 4. Let's welcome the chair of this session, academician Tai Li. Dr. Li, please.
Okay. Let's resume the second half of the morning session. We will have again three presentations. The first one will be presented by Dr. James Schwab. He's a research professor at the University of Albany, New York. His research area has done study work in the atmospheric chemistry and air pollution, with an emphasis on policy-relevant scientific work. And he would have a co-speaker, Sarah Liu. Also, both of them are online. And their presentation will talk about the impact of the pandemic on air quality, economic activity in New York. Let's welcome Professor Schwab.
Greetings from Albany, New York in the United States. I'm going to talk to you today about some selected impacts of the COVID-19 pandemic on New York State. My name is Dr. James Schwab, and together with colleague Dr. Cheng-Hsuan and Mr. William May, we work at the Atmospheric Sciences Research Center at the University of Albany in New York. The areas I want to talk about today are air pollution, economic activity, and politics, and how these have been affected by the COVID pandemic. I want to first start with an abbreviated timeline of the COVID pandemic in New York State. The first reported case of COVID in New York State was on March 1st of this year. little more than 2 weeks later, universities, colleges, and schools began to shut down and pivot to distance learning. Less than a week later, Governor Cuomo shut down all non-essential businesses in New York State. The peak of the pandemic occurred on April 4th in New York, where there was a record of more than 12,000 new cases on that day alone. Little more than a month later, the new cases were much lower, less than 2,000 per day, and mainly in the New York City area. So the phased reopening parts of New York State began on that date. Now we're almost 5 months later, and the current statistics and conditions roughly are about 1,000 cases per day statewide. But we have had more than, or almost 500,000 cases total, and more than 25,000 deaths. So it's quite a large impact here. All regions of New York are partially reopened, but are not engaged in normal activity yet as of this point. The impacts on society that I have chosen to highlight today are air pollution, an area of my expertise, and the lockdowns imposed across the world provided unprecedented experiments in anthropogenic emission reductions. Many papers have been and are being written on this topic. A large impact to society occurred in economic activity. Virtually every sector of economic activity, with a very few exceptions, was greatly curtailed during these lockdowns. Finally, politics. In the United States, all of this is occurring against the backdrop of a highly contentious presidential election. Looking at the ground level air pollution in New York State, I'm going to highlight 3 sites that are run by the Atmospheric Science Research Center. First, at Whiteface Mountain in the Adirondack Mountains, a high elevation remote site. Second, and that's up here. Second is Pinnacle State Park, a rural site in southwest New York. And third is Queen College, an urban site within New York City. The next 3 slides will show you figures from the 3 sites I just mentioned. And they will be showing forecasts of what one might expect pollution levels to be compared to what we actually observed. And the time period for these observations and predictions is from October 2019 through October 2020. The black trace is the data for the pandemic period. The blue line is the forecast for the post-pandemic period. And the shadings represent the prediction intervals, at the 80 and 95% level. So the forecast is what we expect as normal values. And then finally, the red line is the data from March 2020 on, which includes the shutdown and partial reopening periods. With our Whiteface Mountain, our remote site, we looked at 2 of the primary pollutants, carbon monoxide and oxides of nitrogen. Here is the observations leading up to the pandemic, prediction going into the shutdown and pandemic periods, and the CO is noticeably lower than one might predict. Same way with nitrogen oxides, noticeably lower than one might predict. Contrast that with ozone, where there's really no reduction in ozone during the pandemic period. And this is something that other scientists have seen. At our rural site, we show a similar picture for carbon monoxide. It's clearly lower after the shutdown. The red line compared to the model prediction. But interesting and surprisingly, NOx does not show a noticeable change here. We'll see that satellite data does show a noticeable change, but we'll look at that. And then, as with our remote site, no noticeable change in ozone. And then in particle number concentration, total particle number, really no noticeable change in that either. We go to Queens in New York City, and unfortunately there's very little post-shutdown currently available. So if we look at the PM 2.5 going into the shutdown, and then the predicted values, and we see that there's a hint, at least, that those PM 2.5 values are lower, but not really enough data to give us much confidence in that. And the same thing with ozone. Like the other two sites, it doesn't really show a change, but again, not enough data to give us much confidence. Now, if we shift from in situ measurements to satellite retrievals and look specifically at two things satellites are quite good at measuring, which are nitrogen dioxide column and aerosol optical depth. And the aerosol optical depth is a proxy for the amount of aerosol PM 2.5 in the air. Here we see the results for 2019 over roughly a 20-day period in late March and early April, showing the 2019 NO2 column. You compare that to the same period in 2020, and you do get quite different results. Now notice our Pinnacle State Park site was up in this region where there's not a lot of change year to year, so that kind of leads some, makes us believe our in situ measurements a little more. But where was there a change, and how much of a change was there? If one looks at 5 different domains, total eastern U.S., which is the large domain, then the northeastern U.S., and then New York State, the New York City metropolitan area, and the Albany area. So if we go to the next, we can compare all those different areas and see that for each of these domains, 2019 had a higher NO2 column than 2020. So it's consistently lower during the shutdown period, roughly 10% lower overall of New York State, and more like 15% lower in New York City. So there definitely was a decrease in NO2, not as big as some other places have seen, but very clearly different. Here, these next 3 slides are from colleagues at NOAA, and they show the TROP-OMI satellite results for March, and then we'll go for April and May. And on the right side, in each case, you will see a difference, a TROP-OMI difference plot for the NO2 column density, where any place where there's blue means that there's less NO2 column in 2020. And any place where there's orange is actually an increase in NO2 column over that period. And you can see that in much of the eastern U.S., particularly in the metropolitan areas, where there's much less traffic, there was a whole lot less NO2. Now, on these left-hand panels are emissions data, again from a NOAA colleague, showing Los Angeles on the top, New York on the bottom. The month of March is highlighted here in this shaded area, showing a huge drop in emissions for both Los Angeles, and for New York over this period. Now, if we go to this is April, and you can see there's actually more column density increases in much of the U.S. than there was in March. The New York City metro area is still much large decrease in NOx observations via satellite, and the emissions, according to the NOAA models, are starting to come back. And then finally, one goes to May, and again, very minor changes year to year through much of the U.S., but still noticeably lower in 2020 in the New York City area and some other areas of the eastern U.S. And the modeled emissions are coming, at least in California, are coming back to a normal level by the end of May. Finally, in terms of the oxides of nitrogen, this shows the emission changes based on satellite and ground data, looking at how much change there was in NOx emissions. And you can see the decreases again are shaded by blue, the increases by red. And in New York is the state with the greatest decrease in NOx emissions, according to the models. And there are actually places with increases in NOx emissions. And then there's ozone changes, and notice that the NOx emissions go from -50 to +50, whereas the ozone changes go from -5 to +5%. So the ozone is very, very small effect overall. There's increases in some of the urban areas, New York City, Chicago, Indianapolis, Los Angeles, and up in the Bakken gas fields where they're mining oil and gas. So some much smaller changes in ozone, and often with a different sign than one sees. Here's the one slide showing some aerosol optical depth measurements in March of 2019 versus March of 2020. It does show much higher aerosol optical depth in 2020, both in the eastern U.S. and in California. But I think there's a lot more work to be done with this particular measure. Okay, so that's the air pollution impacts. Now, if we go to economic activity, there are definitely many major impacts. Unemployment is very high in the U.S. Gross domestic product, all economic activity came down a lot. Some segments of the economy that were particularly affected were transportation, restaurants, tourism and travel, and all of this had an effect on state, federal tax collections and budgets. The pandemic has had a major impact on employment in New York State, and even more so in New York City. So in New York City alone, even in August, there were still more than 600,000 jobs that had been lost. The hardest hit sectors in terms of job loss were leisure and hospitality. You can see the numbers there. Professional and business services, trade, transportation, utilities, education, and health services. One of the most dramatic changes is the increase in unemployment insurance, government unemployment insurance claims. They went up between 2,000 and 3,000% over the course of a couple of weeks. Quite amazing and challenging for the unemployment insurance government employees. Retail activity also showed some very large impacts. One interesting thing is this little spike due to stockpiling behavior by consumers, followed by a decrease in credit card and consumer activity after that occurred. And you can see that New York City was hit harder and more dramatically, earlier and more dramatically than the rest of New York State. This figure shows a survey of business conditions, and it hit the lowest point in more than 20 years after the lockdown occurred. So businesses were just kind of really, they don't like uncertainty, and this was one of the more uncertain things that has ever happened. New York State budget. New York State, its total budget is about $180 billion. But a lot of that is funds that are specified in certain ways. And so the fund that is controllable by the governor and the legislature is close to $80 billion. And the shortfall for this particular year is roughly $13 billion. So a huge chunk of the budget that is in deficit, which is in principle a violation of the Constitution of the state. Unfortunately, full recovery is something that people here in New York State don't expect until 2024. So the full 4-year budget gap is predicted to be closer to $60 billion, which again is a huge effect. Finally, the 2020 election and politics in the U.S. The presidential election is closely watched around the world and hotly contested here. The incumbent president, Donald Trump, is facing a challenge from the former Vice President, Joseph Biden. The electorate is sharply divided and facing at least 3 major disruptions to their daily lives and well-being. The COVID pandemic, an economic collapse, high unemployment, closure, failure of many businesses, which is itself a COVID impact. Social unrest due to pandemic-related upheaval and racial inequality, which has been highlighted by police killings of unarmed black citizens. So, what are some of the political considerations? Well, there's the economy. Historically, the economy is a good predictor of the outcome. In this case, this predictor favors the challenger, but this isn't an ordinary year, so that's hard to know. Science is on the ballot, I would claim. The incumbent has often refused to believe health experts on the pandemic and climate scientists on climate and other things. The challenger does claim to follow the science. I think you know who I'm supporting. Voting, due to the ongoing pandemic, a much larger fraction of the votes will be mail-in ballots. If the election is close, the results may not be available for weeks or months. And then finally, the federal government response to the pandemic, many believe has been quite inadequate and therefore a issue in this election. So finally, what I will say is that the impacts of shutdowns and lockdowns on air pollution in the atmosphere were relatively short-lived, but the wider impacts on society in terms of economic activity, politics, and other areas is an ongoing and evolving subject, and we will not have a clear picture of these impacts for some years. Thank you very much, and I'll turn it back over.
Thank you very much, Professor James Schwab. Let's welcome this welcome student. Any question on the floor from the floor? You have a question here for you because I noticed that in your presentation this is statistics showing that the emission of the oxide of the nitrogen in most states were significantly lower, but except 2 states. What are the observations? Why these 2 particular states have an increase in the emission of oxides of nitrogen?
I did not hear the question. I was on the YouTube and now I'm back on Google.
Okay, I'm sorry, I didn't hear the first question. I'm just curious, in your presentation, you did statistics about the emission of oxides of nitrogen. In most of US states were all in decrease, but then only except 2. What are the rationale behind it? And I was just curious about it.
I do not have a good answer for you. I don't know. Sarah, do you have any thoughts on why? Montana is very close to oil and gas producing regions. And I don't know if that has anything to do with it. I don't know. I think the other one is like Missouri, right in the middle of the country. And that's really confusing to me. I have no good reason for that.
Yeah, I agree. But I do think the major reduction is actually on traffic. So in the certain metropolitan area, beyond that, a lot of activity actually changed. So I don't know the exact reason, but I do think it's actually a lot of production, whatever social emission pattern actually changed during this period.
Right. I mean, I think that it's definitely, Sarah's exactly right. The traffic was a big change. The thing is that the truck traffic in the U.S., which is a lot of the emissions, did not go down very much. It was more efficient because the roads were clearer, but there were almost as many miles traveled by the diesel, heavy-duty diesel trucks as there was pre-shutdown. So the reason it's only at 10%, and that's something similar to what John Burrows was saying, I think is probably due to the fact that there was, still quite a bit of heavy-duty diesel traffic going on.
Okay, thank you very much. I think the very informative presentation had lots of data associated with it. Your observation about the impact on the Somerset area or in New York is quite interesting. Okay, thank you so very much, Professor James Schwab, and also Sarah Lu. Okay, let's move on to the next presentation. Will be presented by 2 speakers. First speaker is Dr. Chou. I think he's a research fellow from Research Center for Environmental Changes, Academia Sinica. And the second speaker is Professor Ben-Jei Tsuang from National Chung-Hsing University with the Department of Environmental Engineering. They are giving an on-site presentation. Let's first welcome Professor Dr. Chou.
Okay, thank you for the nice introduction, and I do appreciate the invitation from the hosting organization to invite me here to share our observation of the air quality change during the lockdown period in East Asia. At first, I want to share this honor with my co-author, Dr. Cheng-Hsing, Dr. Lin Chuanyao, and Dr. Liu Qianyi. He is our partner from National Central University. Okay, in line with the presentation from Professor John Burrows, I also start from the history of air pollution. Actually, in addition to fighting with disease, we are also fighting with air pollution for a long time. Starting from probably 100 years ago, actually, human beings were experiences with air pollution, and we know that the air pollution was mostly relevant to the combustion of coal and later on petroleum for the purpose of energy. But unfortunately, at that time, people had only very limited data and knowledge to address the impact of air pollution. And nowadays, we are very fortunate to have an array of state-of-the-art instruments on the satellite, just as the story given by Professor John Burrows earlier. That here I show you two examples of the satellite map, showing the distribution of nitrogen dioxide and PM2.5 to maybe the most notable air pollutants at the moment. From the global distribution of the air pollution, actually the data evidence that the impacts of urbanization and industrialization. A number of scientific reports told us that there could be a huge number of premature deaths due to the results of air pollution. All those studies also suggested that human beings need a change in our regular activity to reduce the air pollution. But the question is, what are the changes we need to mitigate air pollution? This is a very difficult question because there is almost no way to carry out an experiment in lab before you get it in the real society. COVID-19 is a very sad event, I would like to say that. But the lockdown on national and maybe even continental and intercontinental scales resulted in a huge reduction in the emission of air pollutants from transportation, business, and industrial activities. This provides us a very rare opportunity for a real-world experiment on the response in air quality to the reduction in air pollution from human activities. Moreover, Taiwan is located at the downwind area of those Chinese megacities, Beijing and Shanghai, for example. And this advantage allows Taiwan Strait to be an ideal location to investigate the influence of Chinese lockdown. So we started from analysis of satellite data sets, just as the story given by Professor John Burrows. All this data was from the Schwab-OMI instruments on board the ESA's satellite Sentinel-5P. A tricky thing here is that because the Wuhan lockdown happened just one day prior to the Chinese New Year Eve of this year, so the reduction in air pollution due to lockdown actually mixed with the regular reduction due to the Chinese New Year. So here we put all the analysis on lunar calendar. Therefore, we can get the effect of Chinese New Year in line from year to year. From all those maps, actually, we found that 1 month before the Wuhan lockdown, actually, nitrogen dioxide decreased from the level of 2019 by around 30% in China area. So at the moment, we have not yet identified a good answer for this reduction, probably due to the changes in meteorology from year to year. But at the case of the lunar January of 2020, we found that a substantial decrease up to 60% reduction over this area that's covering the area from North China to East China. And the interesting observation is that 1 month later, in the lunar February and later on March, the level of nitrogen dioxide bounced back to the normal level and even a little bit overshoot. That's because of the reopening and the resuming of the industrial activity in China. In addition to the nitrogen dioxide, we also look into the changes in other air pollutants like carbon, CO, SO2, and also aerosol optical depth. That's a proxy of PM2.5. The finding is that there is almost no change in the total current level of sulfur dioxide and the CO. This may be due to the discrepancy in the lifetime and the regional background of the species. But if you look into some details, actually, you can find some decrease in CO over the North China Plain, and also some decrease in the sulfur dioxide in the over the Yangtze River Delta. So we still need more work to identify the changes in more detail. But for aerosols or PM2.5, we also found a decrease of about 30% during the lunar January of this year. Then we move to the ground-based observation in Taiwan Strait. Taiwan EPA has 4 air quality observation stations over this area from Jinmen, Mazhu, and Magong, and also the Cape Fugui as the northern tip of Taiwan. We analyze all those data from the 4 stations and the average to represent the mixing ratio of air pollutants over the Taiwan Strait area. Here, the blue bars showing you the average level for 2017 to 2019. That is the previous 3 years to give an climatology level. It's very clear that from the December to the lunar January and then to the February, we had a regular decrease in air pollution due to the Chinese New Year. But this year, as shown by the red bars, a very deep reduction occurred in the January. So this because of the impact of lockdown in China. And the total decrease here in nitrogen dioxide around 50% and 10% due to the Chinese New Year according to the previous observation. So in total, we accounted about 40% reduction due to the COVID lockdown in China. In addition to nitrogen dioxide, we also look into the response in some other air pollutants, CO, SO2, and the PM2.5. Interestingly, we found that the CO response similar to that of nitrogen dioxide because it's also emitted from the transportation, but the amplitude of the reduce is not as strong as that of NO2. We did not see a clear decrease trend in sulfur dioxide because over the last probably 10, 15 years, actually, in Asia, we do have a long-term trend in the decrease of sulfur dioxide, mostly due to the air pollution control measures in mainland China. But anyway, in the lunar January of this year, actually 1.2 ppb, that is the record low of the SO2 level over Taiwan Strait in the last couple years. So we need to do more efforts to do assessments on the reduction of sulfur dioxide, and PM2.5 decreased by around 30%, as in line with our previous observation by satellite data. And also a very important finding here is ozone increased by around 10% during the lockdown period, I mean the lunar January of this year. The increase in ozone is mostly due to the reduce in its chemical sink, including CO and the nitrogen dioxide. But the impact of the increase in ozone could be very huge because ozone is the major oxidant in our atmosphere. In my lab, we regularly collected aerosol samples from two remote stations, one around the Magong city and another at the northern tip of Taiwan, the Cape Fugui. Here is the data for major aerosol species we collected from the field. We found that as the air quality in general improved, but the particulate nitrate and the sulfate actually increased during the lunar January of this year. This obviously disagree with the reduction in its precursors gas, that's nitrogen dioxide and the sulfur dioxide. So we look further into the amount of total nitrogen oxide, for example, that exhibited consistently with the reduction of nitrogen dioxide, as shown here by the blue and red bars. But the tricky thing is, due to the increase in ozone, the particulate fraction of the nitrogen oxide increased by almost 40% during the January of this year. The increase in the particulate fraction of nitrogen oxide could be due to the increase in the oxidation capacity of the atmosphere, as shown by the increase of ozone level during the lockdown period. Our observation is in line with some recent reports published by Chinese scientists. In this report, actually, they indicated that the increase in PM 2.5 and also in ozone over Beijing, and also increase in ozone in Shanghai area. Another study, they estimate the reduction in air pollutant emissions over the whole China area, and here the reduction in CO, nitrogen oxide, sulfur dioxide, and also PM 2.5 roughly agree with our observations. So we decided that this report is credible. So we use this into our digital experiments. We use the state-of-the-art atmospheric chemistry model WRFChem to simulate the response in air quality due to the emission reduction with three scenarios. One is the control one with regular emission. Second one is the scenario suggested by the paper. And third one is a very aggressive one. We cut all the emission by 80%. And this, the upper rows showing your response in CO, and the bottom view panels showing the response in PM 2.5. Obviously, in a typical case of air pollution case, we will receive air pollutant transported from mainland China. But fortunately, in this year, thanks to the lockdown, actually, we have a very mild impact due to the transport of air pollutant during this case. We also looked into some details on the impact of long-range transported air pollution. We calculate the reduction in the nitrogen dioxide for three areas. For the area 1 is for the south region in mainland China. Area 2 and area 3 is the downwind area around Taiwan. The case here is the reduction in nitrogen dioxide, the primary air pollutant, that actually respond consistently with the reduction scenario. That's very straightforward. But for PM 2.5, mostly generated from photochemical reaction in the atmosphere, so we call it secondary aerosols. We found that an aggressive reduction in the emissions cannot help too much to a further reduction, or cannot help to further improvement in the air quality. So with a summary, our observations show that the improvement in air quality due to lockdown and due to the reduction in the air pollution emission over mainland China. But we found increase in ozone and we found increase in the formation of secondary aerosol. So with a strategy of air pollution improvements, we do need further knowledge in terms of atmospheric chemistry to optimize our measures to improve our further life. Thank you for your attention.
Thank you, Professor Zhou. I think we will postpone the questions for later. I think we would next welcome Professor Zhuang Ben-Jei. Zhuang.
Thank you for the introduction. Yeah, this is just a picture I just took about in June in Taichung. So you can see the blue sky and white cloud. So in the summer, I think this summer is a very pleasant summer for like in the past 10 years. We don't have such summer, but this is the first summer we had. So actually people in Taichung, they are very happy with this good air quality. And this is a picture I took like 17 years ago or 15 years ago. So you can see during that time, the air quality is very, very bad. Yeah, sometime in June, it's raining season. You can barely see the mountain. But in September, it's like dry season. Yeah, the mountain is gone. You cannot see the mountain. So this was the day for me in the last 10 to 20 years. But so this summer we are really appreciate such a beautiful summer. So we are thinking it's why this change is due to this like COVID epidemic or not. So usually we think because meteorology is a very important factor to affect air quality. Maybe 70% air quality change due to meteorology change, and 30% is due to the emission change. So we have to separate these two effects. It's a little bit complicated. And so this is the model showing you the green line is simulated by the CMAC air quality model using the we say the 2016 emission data category. So you can see comparing to observations, and most of the time during this just February and March, actually the model is like predict higher concentration than the low concentration than the simulation. It means maybe in February the emission is increasing, but the rest of the years in January or also after March, you can see the model is over predict the concentration. So imply the emission actually decline in the most of the time in the last half years. So this really is showing maybe this change, the air quality become better is really so true. So maybe we should this will become permanent. Okay. And this showing you the half year in mean concentration PM2.5 over Taiwan Island. So this is 19 in 2019, and this become in 2020. So the difference is like 13%. So major reduction of PM2.5 is occur in central Taiwan and southern Taiwan. In Taipei, it's very little decrease. So we do have a much better air quality in this half year in central and southern Taiwan. And this decline actually is occurring in the past 6 years. Each year, the PM2.5 is decreasing and keep decreasing. So this year is the best year in the past 6 years. So this kind of slightly gradually decreasing in the pollutant. And so why this year the air quality become better? So I'm showing you the traffic. So I say the emission because it's really emissions from the traffic and also industrial. It's two major emissions. So you can see in the northern Taipei, and this is the traffic volume in northern Taipei. This from automobile. And this brown is showing the 2020, the vehicle transportation volume. And the blue one is last year, 2019. So you can see after the COVID pandemic breakdown, in northern Taipei, so you can see a slightly decrease in the traffic volume, but it's not too much, maybe only by 5%. But for the buses, there are huge decline in the bus traffic volume. It declined by about 40%. But until last month in August, the bus volume almost become the same as last year. So for this transportation decline, it only occur in the first half year of Taiwan. Okay. But for trucks, it's a major transportation, major source for the air pollutant. And you can see for trucks, it's almost nothing changed. So it means but truck usually they transport the industrial goods from around the Taiwan island. So it means maybe industrial is not showing significant decline because you can see the sign from trucks. Okay, this is central Taiwan. It's very similar to northern Taiwan. So actually there's no, everywhere in Taiwan is similar pattern for the transportation change. And because so we are thinking why this change. Another possibility is because our energy policy, we try to switch the coal from the 45% of electric usage to 30%. So if we change, the government will use natural gas rather than coal for the electricity. So this showing you the our major coal-fired plant. One is Taichung Power Plant, and the power generation in 2020 and last year. So you can see the power generation from the Taichung Power is decreased a lot, maybe by 40% in January. And for another power plant, Sinica Power Plant, is in Kaohsiung. Also, the power generation from this power plant is much less than last year. So this is one of the major reasons cause this air pollutant reduction in central and southern Taiwan. And also we can check the energy usage. The energy usage, the total energy usage for the last first half year in Taiwan is declined by about 6%. So this means the 6% decline in energy usage means will maybe cause the COVID-19 pandemic. So this may be one of the reasons for this better air quality. But another one is we reduce about 2% total energy use from coal and increasing 2% increase in natural gas. So it means this energy switching from coal to natural gas, we can see from the data set. So I would say about 15% reduction in PM2.5 and 43% may be due to the less energy usage. And another 30% of this, we say the air quality improvement may be due to we switched coal to the natural gas. So this could be the major reason. And also we can see the energy distributed to the different industrial section. And for this textile, the energy is lost. And also for the petroleum products and reduction also a lot. So it's like we reduce these two sections, but for this electronic product, actually we use more energy. So it means our society, our our business is switching from like this textile to electronics. So maybe this is a good switch because this transaction make the better air quality because the electronic they consume less cleaner energy, I would say. And we also see those impact from this, we say the indicate pollutant. For vehicle, if it change, then we are showing you the CO and non-emission carbon reduction in these two pollutants. And for industrial, they usually use coal or heavy oil, they will show reduction in SOx. And this showing you the CO in these 2 years, actually reducing about 10% in CO. So it means traffic reduction about 10%. And for non-emission hydrocarbon, we also reduce 10%. So this showing maybe for transportation, we reduce about 10% emission from transportation. And for SO2, we reduce 12%. So it means for the industrial, we reduce 12%. So usually we combine everything and from the local emission, but also Taiwan affected by the long-range transport that Professor Chou was showing. And also in this ocean, Taiwan Strait is very, very busy in this past half year. We have vessels, lots of Navy vessels. So it's different. But so we are still trying to figure out what is the major impact on the air quality. But I would roughly say for the COVID-19 on PM in Taiwan, and maybe it's 30% decline. Maybe 5.7% is due to this primary energy reduction. But for the transportation, actually reduced very little, about 1.8%. And energy consumption is also 0.5%. But another thing is quite important is actually we import lots of crude oil and make it to be gasoline and diesel engine and export to China. But this part also declined a lot. 5.3%. So maybe this is also imply maybe China used less gasoline in the past 6 months. So finally, this is my conclusion. Maybe, yeah, okay, and my talk. Thank you a lot.
Yeah, thank you very much, Professor Zhang. Let's now give the floor to the audience. Any questions? Any questions from the floor? Yeah, I have a question. I have a question for both of you, because in your both presentation, the data seems to be consistent in terms of the emission gases, the emissions, the rate of emission for oxides of carbon and the nitrogen and also PM 2.5. Of course, maybe something good because of this pandemic. But the question, I also noticed that there's an increase in ozone and increase in aerosol. And I don't know whether or not this is, if without the pandemic or after the pandemic, would this increase be worse, or what is it? What is the how come this aerosol and the ozone? I think the rate increase is different. It's different from the other.
Okay. Yeah, actually, ozone in Taiwan also increasing, but PM2 is decreasing. But these two pollutants kind of like they are always go to the other direction in Taiwan. Yeah, usually when the PM2 decreasing, usually the solar radiation become enhanced. They will enhance the photochemical reaction. And ozone is a kind of product photochemical reaction. So this is one of the reasons. And the second reason is because we reduce this NOx. And this NOx also reduce PM2.5 eventually. But there's also like titration effect. Yeah, because NO also absorb ozone. So if we have less NO, then ozone will increase. So but I believe in the future, ozone will decline as well, because in the beginning, they will like kind of go to the other direction, but eventually they will decrease in the future. Yeah.
Sorry. I would like to make something more to the response of Professor Zhuang. Yes, that in the last probably 20 years, actually in Taiwan, we saw a significant increase in ozone level, ozone pollution, and actually at the moment, most of the notable air pollutant, ozone and the so-called PM2.5, actually most of the PM2.5 composed of so-called secondary air pollutants, the sulfate and the nitrate, as I suggested earlier. So in the design of the best air pollution control strategy, probably we should keep very carefully in regulate all the emission of air pollutants, so that we should trying to keep the increase of ozone within an allowance region, so that we will not, because of ozone, resulted in very worse air quality situation. That's my comment. Thank you.
Okay, thank you so very much. Any other questions from the floor? If not, this thank both speakers, Professor Zhang and Dr. Zhou. Thank you very much. Okay, let's move on to the last presentation will be given by, it's a video presentation, will be given by Dr. Simon Liu. I think he's an associate administrator of Agriculture Research Service, U.S. Department of Agriculture. And Dr. Simon Liu, I think he was previously he was a director of the National Agriculture Library and associate director of the National Library of Medicine and the chief information officer. I would welcome this presentation be recorded by Dr. Simon Liu.
Good morning, Taiwan. My name is Simon Liu, and I am the Associate Administrator for Research and Management and Operations at the Agricultural Research Service in the U.S. Department of Agriculture. I thank you for the invitation and appreciate the opportunity to talk to you from Washington, D.C. Now I'd like to share my screen so that you can see my presentation slide. In the past 9 months, COVID-19 has had a tremendous impact around the world across many different industries, such as healthcare, airlines, train operators, and others in the transportation industry, hotels, restaurants, and other hospitality and entertainment industries, as well as sport, education, and of course, agriculture. It is my distinct pleasure to share with you about the impact of COVID-19 on agriculture and the potential research responses. COVID-19 impacts many sectors across the agriculture industry. This slide shows major challenges we face and some key questions we need to answer. First, food safety in general and food processing in particular. Is our food safe to eat? What is the effectiveness of our food processing protocol to eliminate COVID-19? Are there rooms for improvement to increase food safety? Second, food security and pricing. Do we have enough food to share? Are there areas where food are not available? Any major differences among the regions in terms of food availability and pricing? Third, animal health and production. How to protect the health and safety of our domestic and agricultural animals. How to manage our food animal productions and supply chain. Next, economic impact. What economic impacts on the agriculture and food supply chain? How did the pandemic affect the macroeconomy and factors impacting U.S. agricultural export? How did the shelter in place and social distance impact the agricultural labor market? Given all those impacts A key question for us is how best to respond to those challenges. What kind of research responses do we need to have to address critical cross-cutting issues to protect our food supply chain? Before zooming into specific research, I'd like to take this opportunity to give a brief overview of my organization, the Agricultural Research Service, ARS. ARS is the largest agricultural research institution in the world. Our mission is simple: deliver scientific solutions to national and global agricultural challenges. Our vision is clear: global leadership in agricultural discovery through scientific excellence. We have 8,000 strong employees, which include 2,000 plus PhD research scientists and postdoc doctors, as well as 6,000 plus research supporting employees. Our employees are located in 90 plus research laboratories in 40 plus states throughout the country and 4 overseas locations. Our annual budget is about $1.5 billion, which is appropriate fund, and $150 million of self-fund. Currently, ARS has 690 research projects, and we organize our research project under 15 national programs in the next slide. The national programs serve to bring coordination, communication, and empowerment to research projects carried out by ARS. The national programs have focused on innovations, relevance, impact, and quality of ARS research. Those 15 national programs are further organized into 4 program areas for effective management and coordination. The program areas include animal production and protection on the left column, crop production and protection in the second column, nutrition, food safety and quality, and finally, nature resources and sustainable ag systems on the right column. As I mentioned earlier, we have 90 plus research labs in 40 plus states around the country. Each and every one of them is highlighted as a white circle on the map. Our current SARS-CoV-2 research falls primarily under the animal production and protection area. ARS has 30 plus labs conducting animal production and protection research. Most of those research labs are at biosafety level 2, and a few of them are at level 3 or 4. This map highlights our 4 major high containment research labs. First is the Prime Island Animal Disease Center at Orient Point, New York in the Northeast. This lab focuses on vaccine development for major animal diseases such as foot-and-mouth disease, African swine fever, and others. Down the southeast is the U.S. National Poultry Research Center at Athens, Georgia. This lab is designed to respond to high pathogenic avian influenza outbreak. It also responds to Newcastle disease, West Nile virus, and other emerging viruses of poultry and other birds. In the middle of the country is the National Animal Disease Center at Ames, Iowa. This lab conducts basic and applied research on selected animal diseases of economic importance to the U.S. livestock and poultry industries. Also in the middle of the country is the National Bioagro Defense Facility at Manhattan, Kansas. This is a new state-of-the-art biosafety level 4 research laboratory. The U.S. government invests $1.25 billion to build this facility, which is scheduled to complete in the next 2 years. The lab is designed to protect the nation's agricultural systems and the stakeholders against the threat and potential impact of serious animal diseases. Now I'm going to zoom into a few SARS-CoV-2 research projects we have. Those research projects are designed to answer the following key questions. By the way, those questions are not intended to be comprehensive of all the topics that are relevant to SARS-CoV-2. The first question is, can agricultural animals become infected with SARS-CoV-2? If so, can infected animals transmit the viruses to other animals and or humans? That is a really important question, as we often so close to food and domestic animals such as cows, pigs, dogs, cats, and others. Second, can we develop animal models to support the development of SARS-CoV-2 medical countermeasures such as vaccines and drugs to protect people or livestock from COVID-19? 3, can mosquitoes and other blood-feeding insects transmit the SARS-CoV-2? This is a really valid question. 4, what is the environmental stability of SARS-CoV-2 associated with transportation and marketing on raw food? 5, what is the effectiveness of food processing protocols to eliminate SARS-CoV-2? Do we need to take different actions or use different techniques to protect our food supply? Finally, question number 6. Can other viruses be used as a model to study SARS-CoV-2? From a technical perspective, SARS-CoV-2 has to be handled in a biosafety level at least 3 facilities. Just for your information, we have more than 100 level 2 research laboratories with only a few level 3 or 4 labs in the country. So if we could find a good surrogate, less hazard, which can be handled at level 2 laboratories, then we will be able to expand our research capacity on this topic. Doing so, we hope to get to some solutions soon. This slide shows research related to question number 1. Can agricultural animals serve as a source for SARS-CoV-2? And if so, can they amplify the virus? Currently, we have research project on this question at 2 locations. First, at the U.S. National Poultry Research Center in Athens, Georgia. The research focus there was to determine whether chicken, turkey, quail, duck, goose can be infected with SARS-CoV-2 and potentially become a source of further infection. Based on our research so far, poultry species are not susceptible to infection with either SARS-CoV-2 or MERS-CoV. The second study was at the National Animal Disease Center in Ames, Iowa. The research in partnership with Cornell University was to determine or confirm whether pigs, cows, and deers can become infected with SARS-CoV-2 and potentially become a source of further infection. Again, based on our research so far, pigs and cattle have low risk of becoming infected. Deer studies are still ongoing. So far, there's no clinical signs of infection. Moving on to key question number 2. Can we develop animal models to support the development of SARS-CoV-2 medical countermeasures, such as vaccines and drugs to protect people and or livestock from COVID-19? As I mentioned in previous slide, livestock and poultry tested. So far, they show no clinical signs of infections, and as a result, they are not good animal models. On the other hand, our tests indicate that ferrets, cats, golden hamsters are susceptible and can be used for SARS-CoV-2 research, looking at vaccine development and countermeasure drugs to help to combat the virus and support rapid recovery. The research is ongoing, and we are anxious to see result. There were some speculations that mosquitoes may be able to transmit the COVID-19 infection. So we did some work in Kansas with Kansas State University. We were able to confirm that not only mosquito, but also biting midget are not susceptible to SARS-CoV-2 infections and not able to replicate the virus or transmission. I do want to mention that we also look at housefly. We study if they were on a surface that were contaminated with SARS-CoV-2, could they then transmit the virus mechanically? We have some evidence that the viral RNA particles was transmitted. However, we are not able to propagate the virus, so there's still some work to do in this area. So in terms of environmental stability of SARS-CoV-2, on question number 4, this question related to if a virus was on a surface, how long would this virus survive? We started some of the work at the U.S. National Poultry Research Center in Athens, Georgia. There was some concern about the potential impact to the food industry, so we are currently engaging with stakeholders and trying to have more stakeholder support for this work. In terms of survival of the virus on different surfaces, in general, Department of Defense and Department of Homeland Security, they have done quite extensive research looking at different type of surface, so that that type of research is available. As far as question number 5, what is the effectiveness of food processing protocols to eliminate SARS-CoV-2? Our research in this area started with investigating the antimicrobial washes on poultry carcass under different processing conditions. The work we have done was to determine how to neutralize some of those antimicrobial wash. So before you could actually evaluate the effect of antimicrobial wash on the virus, after sampling the surface of the carcass that have been rinsed, there has to be a neutralization stage where the antimicrobial wash is neutralized, or else the virus would not be able to grow. So our works were to determine the best way to neutralize antimicrobial compounds. Further work is ongoing to look at the survival of the virus on carcass after washing. For question number 6, can surrogate virus, which are less hazardous, be used as a model to study SARS-CoV-2? We initially look at the infectious bronchitis virus. This is another coronavirus, and we feel that it will be a good surrogate candidate. However, what we have found is that infectious bronchitis virus is hard to grow and does not do well at the typical environmental condition where we are finding a SARS-CoV-2 survives. So, infectious bronchitis virus would not be a good surrogate, and we'll start looking for other potential coronavirus surrogate. If you have a better candidate in mind, please let me know. I'm looking forward to explore the idea with you. This slide provides a summary of our initial findings from those research projects. First, poultry species are not susceptible to infections with either SARS-CoV-2 or MERS-CoV. The conclusion was that those common poultry species, such as chicken, turkey, duck, geese, quail, they are not susceptible to infection to either virus. Second, livestock species, such as cattle and swine, they pose minimum zoonotic health risk for SARS-CoV-2. Infection study with bovine was conducted at National Animal Disease Center at Ames, Iowa, and necropsy. All pigs appear normal with no gross lesions. Third, while the deer infection study with SARS-CoV-2 is ongoing, no clinical signs detected. Laboratory tests of tissue samples still underway. Finally, mosquito and biting midget do not transmit SARS-CoV-2. Research confirmed that the mosquito and the biting midget are not susceptible to SARS-CoV-2, oral infections, and replication. I'd like to end my presentation with our future research direction. Our national program for animal health is now developing new research plans and objectives. The focus of our research will be on emerging zoonotic coronavirus and influenza viruses, such as H5N1 and H7N9, so that we can increase our ability to predict the arrival of new pathogens with pandemic potential. Thank you for the opportunity, and this concludes my presentation. I look forward to questions you may have. Thank you.
Thank you very much, Dr. Simon Lu. I think Simon is online for questions. Are there any questions from the floor? Now, I would like to mention that you at the end you mentioned about this research areas. I wonder whether or not those or the comments that you observe here at the work you do at the Agricultural Research Service, would any of those here be applicable here at the our Agricultural Council, or any recommendation that you recommend us to do?
Well, thank you very much. Can you hear me?
Yes.
All right. So first of all, I know I'm the only person that between you and the lunch, so I will make it short. So thank you for the questions. Indeed, we do have collaboration between ARS and the COE in Taiwan. So the animal diseases research, we have strong collaborations, especially at the vaccine development for avian influenza vaccine or animal like the foot-and-mouth disease vaccines. So the answer is yes, there's some opportunity not only now but also in the future for further collaborations.
Thank you so very much. Okay, this there no other questions? Yeah, well, thank you again for staying up so late for giving this presentation. Thank you so very much, Dr. Simon.
All right, thank you.
Well, let's conclude this session now.
Thank you, Dr. Lee. And ladies and gentlemen, before we end our symposium, I would like to invite Vice President Fudong Liu on behalf of the symposium committee members to give a few closing words. Let's welcome VP Liu.
Well, thank you. Thank you very much for staying till the very end. This has been a very successful symposium, data-rich symposium. I myself learned a lot. I hope you did too. Obviously, the topic of COVID-19 is of interest to many, as reflected by the number of registrants. So we set the upper limit for of registrants to attend in person to 240, and we almost filled all the slots. Then we accepted over 70 on-site registrations. We have over 330 who registered to attend online. So together we have over 630 registrations. And we have so many leaders from international societies and academic organizations who shared with us their views and up-to-date information. Also, many investigators who shared with us their state-of-the-art investigations related to COVID-19. I would like to thank them for their participation in this symposium, either in person or online, out of their very busy schedule. It looks like the pandemic will be with us for a while, unfortunately. Thus, the content of many of the presentations will provide important insights on how we deal with this infectious disease, either through the policy-making process or through scientific investigations. I believe even if the pandemic is over, much of the accumulated knowledge from ongoing research and on continued research will be very, very valuable in the unfortunate event that the world is struck again by another similar pandemic. I think a number of speakers shared this viewpoint in their presentations. A few months ago, when we decided to organize this conference, our thought was to facilitate the interaction and the collaboration among many of the 15 societies that are members of CODATA Taiwan. The topic COVID-19 indeed is suitable for this purpose, and I hope we accomplish this goal through this symposium. I also hope we will organize other meetings in the future for the same purpose. In this regard, I would like to thank President Mons and Executive Director Simon Hodson of CODATA for their support of this conference from the very beginning, and for their participation in the symposium by giving presentations. I would like to thank many who contributed to the event, including my co-chair, Dr. Der-Tai Lee, 3 other committee members, Dr. Andrew Wang, Dr. Tinglei Zhong, and Dr. Linzi Chen, who is also director of our Department of Information Technology Service at the Academic Sinica, and was instrumental in the critical information technology support aspect of the symposium. The former 2 I mentioned those above also helped chair 2 of the sessions, and so did Dr. Fan Li, who chaired one of the sessions. Special thanks to Ms. Sui Li, she's still here, who worked extremely hard during the preparation of this conference. In fact, I believe she didn't take any time off during this past Mid-Autumn Festival holidays. So I think Dr. Li should let her take a few days off. I'd like to thank those from Department of Information Technology Service, Department of Academic Affairs and Instrument Service, Department of International Affairs, and my own laboratory for their assistance. Finally, thank you all for your participation, either in person or online. Okay, just one more note. For those of you who joined the conference online, or actually in person also, if you have questions for the speakers, please submit them through the web page. We will forward them to the speakers and then post the answers on our website. We will also plan to organize and compile all the speakers into one file and make it available on our website of CODATA Taiwan. So stay safe and well during this pandemic and beyond. Thank you.
Thank you very much, Vice President Liu. And with this, all the program of the International Symposium on COVID-19 has been completed. I thank you very much for your kind attendance for the past 2 days. And before you leave, please pick up your lunchbox at the registration desk and return your name badge to the desk as well. And may all of you have a nice day. Goodbye.